So today we're going over 3.2, which is polynomials and their graphs. So vertex to standard form. We're going to start off on how to solving them. So you start off by rearranging everything. So the easiest thing would be to expand everything and then combine like terms. So you would do f of x equals -2, and then x plus 3 minus 7. So you FOIL out the x plus 3, so you end up with -2. It's going to be x squared plus 6x plus 9, and then minus 7. Then you can go ahead and distribute that 2. So you would end up with -2x squared minus 12x minus 18 minus 7. The last step would be to combine like terms. So you end up with an f of x is equal to -2x squared minus 12x minus 25. And then this would be your final answer. From vertex form to standard form, the main thing is to distribute and expand as much as you can. If you see the number 2, I'm going to leave this one up here as well as I work on number 2. You're going to expand the x minus 8, so you get g of x equals 1/4, and then x minus 8, and then plus 6. You FOIL the x minus 8, so you end up with 1/4 times x squared minus 16x plus 64 plus 6. We distribute that 1/4, and you end up with 1/4 x squared minus 4x plus 16 plus 6. So your g of x is 1/4 x squared minus 4x plus 22. Now, as I distributed that 1/4, I also simplified. If you want to take it in 2 steps or 3, you guys can do that. I just simplified it earlier for space. So it's saying, given a point and the vertex, write the quadratic equation in vertex form. Now, this is vertex form. So because that is vertex form, all we have to do is going to plug in the numbers and figure out what we're missing. So following vertex form, they're telling us that the point of the parabola are -4 and 7. So this is your x and this is your y. Or in other words, if you don't want to call it y, it's going to be your entire f of x. And then you have your vertex, which is your h, and your k. Now let's plug in what we have. We have the 7 for the f of x. It's going to be 7 equals, we don't have an a, so I'm going to write a. And then parentheses, we have an x, -4, minus your h, which is 1, squared. Oh, guys, real quick, the vertex form should be squared. I didn't realize it's not written, so please just make sure you write it right here. The vertex form is squared. You have -4 minus 1 squared, and then your k, which is going to be plus 5. Now, for you to be able to solve for a, you're going to have to simplify everything and solve for a as you normally would. So it's going to be 7 is equal to a, -5 squared plus 5. So it's going to be 7 is equal to 25a plus 5. I'm going to go ahead and subtract the 5. So I get 2 is equal to 25a. I divide by 25, and we're left with 2 over 25 as your a. So your a is equal to 2 over 25. Now, why is that important? Now we have the vertex and the a, so we can officially write it in vertex form. So we can say, well, f of x, is equal to the a that you found, so 2 over 25, then parentheses, x minus the h, so minus 1, squared, plus the k, plus 5. So this would be your final solution. So you have to find A in order to write it into vertex form. So doing the same thing for question number 4, we have our x and our y, or our f of x, which is 2 and -9. And we have our h and we have our k for the vertex. So we're going to go ahead and plug it in. -9 is equal to A, which is what we're trying to find. And then parentheses, you have your 2 minus the -3 squared plus 6. So let's fix that. So it's going to be -9 is equal to A, 2 plus 3 squared plus 6. That's -9 equals A, 5 squared plus 6. It's going to be -9 is equal to 25A plus 6. I'll subtract the 6 on both sides. And we get -15 is equal to 25A. I'll divide by 25, and that's going to simplify to A is equal to -3/5. So after we have that, we're able to write the equation. So it would be f of x is equal to -3/5. Then x plus 3 squared plus 6 as your final answer. So you have polynomial functions. We often refer to polynomial functions simply as polynomials. Now the following polynomials has a degree of 5, leading coefficient of 3, and a constant of -6. So just so you guys remember, the degree is based on the highest exponent of the equation. Right now the highest exponent is 5, so that's why it's a degree of 5. The leading coefficient is the coefficient that is with that leading term, so it's going to be 3. And then the constant is the number that does not have a variable with it. So we have the leading degree, which is 5, the leading coefficient, which is 3, and the constant, which is -6. Now you have a bunch of coefficients. We usually just care either about the leading term or the leading coefficient, which is again the one that is with the degree. So with the highest degree is the one which is going to be the leading term and the leading coefficient. You put this in standard form, that's why it's going to go from 5 to 4 to 3 to 2 to 1 to no degree on the x. So to 0, which would give us the -6 by itself. So here we have our polynomial functions, and then the table lists some more examples of polynomials. So they give you all of these polynomials right here, and then they're telling us what is the degree. Again, the degree is based on the highest exponent, so degree of 1. The highest degree is at x, which is just a value of 1. For the next one is 2, that the highest degree of the exponent is 2. For the 3 is the 3. For the 4 is the 4. They're asking you for the leading term. So for the leading term, it's going to be the entire term that has that x. So it's going to be 4x, x squared, 2x cubed, and -5x to the 4th. Then they're asking you for the constant. The constant would be the one, like usual, that doesn't have an x. So for that second polynomial, notice how there is no constant, so we write 0. Now, if a polynomial consists of just a single term, then it's called a monomial. For example, you have px is equal to x cubed, and q of x is equal to -6x to the 5th. Those are monomials. Now, monomial just means one term. Mono means one. Binomial. So binomials is two terms. Bi means two. Trinomial means three terms. And again, tri means three. And then you have polynomials, which is the term we use when it's 4 or more terms. And poly means more than 4, so 4 or more. So please keep that in mind. You guys saw this at some point during algebra. If you didn't remember, that's why I mentioned what each prefix of the word means. But just so you guys know what monomial, binomial, trinomial, and polynomial mean. So if you look at it, we have the very first polynomial is going to be a binomial. The second is going to be a binomial. The third right here is going to be a trinomial. And the fourth one from the chart is going to be a trinomial. So they're all considered polynomials because it's more than one term, but technically they have a more specific name. So graphing basic polynomial functions. The simplest polynomial functions are the monomial functions, which is going to be the term either with a value of 1 for the n, 2, 3, 4, 5, 6. Those are the easiest to graph. Why they're the easiest to graph? Because when you have an odd exponent, so for example, if you have a 1 right there, that's considered an odd exponent. So 1, 3, 5, 7, 9, 11, all those are considered odd exponents. So you can deal with your end behavior. I'm just going to call it EB for end behavior. They're always going to be opposites. And if you have an even, kind of like an x squared, again, 2, 4, 6, 8, 10, 12, 24, 64, whatever number it is, as long as it's even, your end behavior, it's going to be the same. What do I mean by that? For an odd function, if it's a positive odd function, it's always going to go, if you go from left to right, it's just going to point down and then up, as long as it's a positive odd function. If it be negative, then it's the opposite. It would be from left to right, up, and then down. But you guys know that based on the reflection over the x-axis. Now, for the even functions, they're always going to look up for the end behaviors, as long as it's positive. So, if you have an odd, let's make a little chart. If it's positive, it's going to be down, up. And if it's negative, it's going to be up, down. And then for the even, if it's positive, it's going to be up, up. And if it's negative, it's going to be down, down. Again, this is all based on the reflection over the x-axis, which are the different types of transformations. EB means end behavior. So we have C, D, and E, which is y is equal x cubed, x to the fourth, and x to the fifth. Notice how this one is a positive odd coefficient, and it's going down, up. So the end behavior is opposite. Notice how for D, it's even, and they're both going up. It's a positive even function. So this is the end behavior. It's going to be the same. And then for the positive odd, again, since odd, it's going to be down, up. So that means the end behavior is going to be opposite. So as the figure suggests, the graph of p of x, x to the n has the general shape of the graph of y is equal to x squared when n is even, and the same general shape of a graph of x cubed when n is odd. Now, if you ever forget, just as a general rule of thumb, which way each part point graph a linear function, you're going to get a positive line like this. So you know the end behavior is going to be down, up from the left to the right. And if you forget the even and you graph an x squared, you know it's going to either look up or down depending if it's positive or negative. And the end behaviors are always going to follow that. No matter what, if it's odd, it's always going to follow the same behavior of the linear x, or just x to the first power for the positive. And if you were to mirror it over the x-axis or the negative, it will follow the same end behavior. Same for the x squared. If you were to flip it over by a negative x squared, negative x to the fourth, it will follow the same behavior. So if you ever forget, you can always use the basic equations that you guys are used to and then work your way around it. Now, what is the whole difference between an x squared, an x4, an x 1, 3, 5, 7? This is the difference. As the degree of n becomes larger, the graph becomes flatter around the original and steeper elsewhere. So if you have an x to the first, you have a graph that looks like this. If you have an x to the cubed, you have a graph that looks like this. So you see how it's slowly getting flatter, but if you have an x to the fifth, I'm just doing an example, you're going to get it even sharper, then flatter, then sharper. Now, of course, I am exaggerating this drawing so you guys get the idea. That's what happens with the exponent gets larger, but the end behavior stays the same. Same if you have an x squared. The x squared, you have a typical looking thing like this, something you're used to. If you have an x to the fourth, it's going to be the same end behavior. It's going to be flatter and then back up. If you have an x to the sixth, just going to be, again, sharper in the edges, flatter on the bottom, and then just going to go back up. But the end behavior is exactly the same. Again, I'm exaggerating the drawings just for purposes, learning them. But just to prove my point, it is the exact same behaviors. So, for example 1, they want us to sketch the graph of the following functions. I'm also going to write the transformation so it makes sense on how to graph it. Now, I am going to do a little bit, let's say x cubed is going to look like this, x squared. Again, these are the positive typical functions. Now, why am I doing that? Because some of these are negative, so I want you guys to make sure you understand how they work. So for A, we have, first thing to note, is reflection over the x-axis. And because it's odd, we're going to have the end behavior to be opposite. So if I were to graph this again, this is just a sketch. Instead of going down, up, because we flip it over the x-axis, it's going to be the opposite, up, down. Again, from left to right. So that graph is going to look like that. We just reflect it over the x-axis. Now for B, it's an even, so the end behavior is going to be the same. It's going to be, it's going to move to the right 2 units, but that's all that's happening. So if you were to sketch this one right now, instead of putting the vertex in the center, you put it right over here, 2 units to the right, and just sketch the typical x squared graph that we know and use all the time. Now for C, we have a couple things happening. We have a reflection over x-axis. We have a vertical stretch of 2, or by 2. We have, we move 4 units up, and the end behavior is opposites because it's an odd looking graph. Now I'm going to draw both of them in the same idea. So your typical one's going to look like this. Now the new one I'm going to graph in red. Now they're telling us we move 4 up, right? So we're going to start here. We have a reflection, so instead of going down, up, we're going to go up, down. And we have a vertical stretch, so it's going to be just a bit steeper. So it's going to look something kind of like that. So the same graph, just flipped over and moved up, stretched vertically by a factor of 2. Of course, I'm not plugging numbers in. If you were to plug in numbers in, it will give you a better looking graph. This is just kind of a sketch of what happens from one to the other. So graphs of polynomial functions and behavior. So the graph of polynomial of degrees 0 or 1 are lines, and the graphs of polynomials of degrees of 2 are parabolas. So the greater the degree of the polynomial, the more complicated the graph can be. However, the graph of a polynomial function is continuous. So this means that the graph has no breaks or holes. So this and this wouldn't happen. They're going to be a one continuous smooth line. So this would not be the graph of a polynomial function. Now, moreover, the graph of a polynomial function is a smooth curve that is, it has no corners, no sharp points, cusps as shown in figure 3. So, it has a cusp, so a point, it has a corner, So that is not a graph of a polynomial function. Now, figure this one, I guess 2 and 3 of this problem or this example are polynomial functions because there are smooth and continuous functions all throughout. Now we are going to learn how to graph the middle part. For now, we're talking about just end behaviors, but you will learn how to do the middle part. So for now, just worry about the end behavior. So the graphs of polynomial functions, again, end behaviors. The domain of a polynomial function is a set of all real numbers, so we can sketch only a small portion of the graph. However, for values of x outside the portion of the graph we can draw, we can describe the end behavior of the graph. So the end behavior of a polynomial is the description of what happens as x becomes larger in the positive and negative directions. To describe the end behavior, we use the following arrow notation. So what's the arrow notation? It's going to be as x becomes infinity. So that's the arrow notation. X reaches infinity, which is the largest. The meaning is x goes to infinity. That is x increases without bound. And then we have x towards negative infinity. That means x goes to negative infinity. I'm going to write neg for negative. Infinity, that is x decreases without bound. So if you look at the completed notes, this is very nicely written in print. But that is what it says. So the end behaviors of the polynomial p of x equals an x to the n plus a n minus 1 x n minus 1 plus in between part a1x plus a0 is determined by the degree n and the sign of the leading coefficient a of n as indicated in the following graphs. So we have this first graph where p has an odd degree. So the part in the middle is dashed because we have no idea what the degree is. We just know it's odd. So we have y approaches infinity as x approaches infinity. Oops, that's an 8. Infinity. That is for this section right here. So the end behavior is the opposite. So again, false left and rising right. So down up, down on the left, up on the right. So as x reaches infinity, f of x reaches infinity, and as x reaches negative infinity, f of x reaches negative infinity. Now what is that? Let me write it in a different color so you can see it better. What does this mean? As we look at x reaching positive infinity, we're going to the right. The y value also increases to positive infinity, and as x reaches negative infinity, the y value is reaching negative infinity. So they work together. Same for this one. We have the end behavior is opposite. So it, in this case, rises, or rise left, fall right. Or if you do up, down, this is going to be a negative x. I'm going to say cubed. I just make sure that this needs to be odd. So as x reaches infinity, f of x reaches negative infinity. It's negative because it's as the x is going to positive infinity, the y is going down. And as x reaches negative infinity, so towards the left, our y is increasing. So it's going to reach infinity. All right, so for the even degrees, now because this is even, we know the end behavior is going to be the same all the time. So if it's a positive, it's always going to look up, up. So rise left, and then rise right. So as x increases, reaches infinity, so again towards the right, we're going to go towards positive infinity. And as we reach the x value to negative infinity, which is towards the left, our y value is also going to be positive infinity. For the next one, which we have a downwards even, so it's going to be same. It's going to be fall left and fall right. It's going to fall no matter what. So when x is approaching infinity, the y is negative infinity. As x approaches negative infinity, the y is negative infinity. So here they want us to determine the end behavior of the polynomial. So we have p of x is negative 2x to the fourth plus 5x cubed plus 4x minus 7. What am I going to look at? I'm going to look at the highest degree coefficient. In this case, it's an even. And the next thing I'm going to look at is if it has a positive or a negative. So that means this is, first of all, reflected over x-axis. And we also know it's even, so the end behavior is going to be the same. So how am I going to determine the end behavior? It's going to look downwards. So it's going to fall left and fall right. So writing it in the notation we've been doing is as x reaches negative infinity, in this case p of x reaches negative infinity. And as x reaches positive infinity, p of x reaches negative infinity because it falls left and it falls right, or it's going down, down. Now let's look at the next one. We have a negative. Actually, no, ignore that. Our highest degree is 3, and it's a positive. So the end behavior, it's going to be opposite. Usually the end behavior for an odd positive is going to look down, up. So it's going to fall left, rise right. So again, the middle part doesn't really matter because we don't know how to solve for it yet. Let's just care about the end behavior. It's going to look like that. So we're going to say as x reaches negative infinity, f of x is towards negative infinity. As x reaches positive infinity, f of x reaches infinity because it's falling to the left and rising to the right. Now, just as the general rule of thumb, to make it easier on yourself, if it helps, always rewrite the equation in standard form. That is the only way to be able to tell from the very first, just what the first term is the behavior of this graph. I should have done that before I started. I'll do it for the next problem, but I caught myself noticing there was a 3 on the second term. So don't make that same mistake. It's actually a very common mistake if you don't rewrite it that you miss the right coefficient. So the last one. So following my own advice from the last one, I'm going to write this in standard form. Okay, and when I do that, I notice a few things. We have a negative and we have a 5. So this is an odd function. So that means the end behavior is going to be opposites. And because we have a negative, it's going to be reflected over x-axis, over the x-axis. So if you were to kind of draw the graph, instead of going down, up with like the one next to it on the left, it's going to actually be up, down. And again, the middle part doesn't matter to us yet. So how are we going to write this? As x reaches negative infinity, g of x reaches infinity. And as x reaches positive infinity, g of x reaches negative infinity. This is because it's reflected over the x-axis. Notice how it's the exact opposite of the second problem we did on this slide, because one's positive, one's negative. So that reflection does matter, and it does change a few things. On how to find the zeros of the graph and how we're going to use the zeros of the graph for the polynomial. So if p is a polynomial function, then c is called a zero of p if p of c equals 0. In other words, the zero of p are the solutions of the polynomial equation. So kind of like how you would factor it usually. P of x is equal to 0. Note that p of c is equal to 0. Then the graph of p has an x-intercept at x is equal to c. So the x-intercepts of the graph are the zeros of the functions. So if p is a polynomial and c is a real number, then the following are equivalent. C is at 0 at p. X is equal to c. The solution of the equation p of x equal to 0. X minus c is a factor of p of x. And c is an x-intercept of the graph of p. Now, as we do examples, this will make a little more sense. But basically, the zeros are when you factor the equation, which is the way you guys have been doing the entire year so far. Those are considered the zeros. That is when either crosses or bounces off of the x-axis. Those are called multiples, but you guys will learn about multiples further into either this lesson or next section. But for now, let's just figure out what the zeros are. So to find the zeros of a polynomial p, we're going to factor and then use a zero product property. So for example, to find the zeros of p of x equals x squared plus x minus 6, we factor p to get p of x equals x minus 2 and x plus 3, which is stuff that you guys have done. How do we find the zero? We find the zero the same way we've been doing it. We grab each parentheses and equal it to 0. And when we do that, we're going to add the 2, and we get x is equal to 2. We're going to subtract the 3, and we get x is equal to negative 3. So these are the zeros of the equation. So it's an x-intercept, so it's going to be 2, 0, and negative 3, 0. So from this factor form, we can easily see that 2 is a zero of p, because we just solved for it. So x is equal to 2 is the solution of the equation. So x minus 2 is a factor of x squared plus x is minus 6. And 2 is the x-intercept of the graph p. And the same thing applies for negative 3. Now, if they by any chance at some point they're going to give us, these are the zeros, find the equation. I believe this is not for this section. But the way you would do it is you're going to grab, they tell you, well, let's say they tell you x is equal to 2. So you're going to grab, well, x is equal to 2. You want to make sure that it's equal to 0. So you would subtract the 2 and you get x minus 2 is equal to 0. You just got one of the factors. So you would work backwards if they give you the intercept in order to get the equation. But right now we're working with the equation to the factor. So the guidelines for graphing a polynomial function. You have the zeros, which are the factors of the polynomial to find all its real zeros. These are the x-intercepts of the graph. So you can test different points to make it, so you can make a table of values to find the polynomial. Include the test points to determine whether the graph of the polynomial lies above or below the x-axis on the intervals determined by the zeros. Include the y-intercepts in the table. So if you have something like the other point, which was 2 and negative 3, for the x-intercepts, let me write that outside. You would want to test out, or test, for example, 1. You can test out 1. You can test out 0, negative 1. Just a few points in between to see which way, if it's going to stay under or bounds or go through the points. Now, of course, it also determines the, we also deal with the end behaviors, which is step 3. Which after you determine the end behaviors, you should be able to graph the equation a lot closer to what the graph is going to look instead of what we were doing earlier. And then for the last one, you're going to plot the intercepts. The x and the y intercepts would be great points to graph. And then you find the points that we use in the table and sketch a smooth curve that passes through those points and exhibits the required end behavior. So they want us to find the zeros and graph the polynomial function. So let's find the zeros. We have a. So the zeros, we're fine solving a typical equation. So the first thing I'm going to do is take out the greatest common factor. So it's going to be x. So it's going to be x squared minus 2x minus 3. Now I can find factors that will multiply to -3 and add up to -2. So 1 and -3 work perfect. So we have x, we have x plus 1, and x minus 3. All of that equal to 0. So we have to set up each term into an equation equal to 0. So we're going to get the first term, x is equal to 0. The second term, x plus 1 is equal to 0. And the third term, x minus 3 is equal to 0. So I will subtract the 1 on both sides, and we get x is equal to -1. I'll add the 3 on both sides, and we get x is equal to 3. So here we have our 3 zeros. 0, -1, and 3. Now, in order for me to graph this, I think I would also like to find the y-intercept. So when I plug in this equation, I'm going to plug in 0 for everything that has an x. And when I do that, I end up with 0. So our y-intercept is also, it's going to be 0, 0. We have the x-intercept at 0, 0, at -1, 0, and at 3, 0. So again, this is going to be a very rough sketch. Okay. So we're going to plot the point 0, 0. -1, 0, and 3, 0. Now they're telling us that it's an odd function, so that means it's going to be, the end behavior is going to be opposites. Now this is a positive one, so it's going to be down on the left and up on the right. So I'm going to do this, and I'm going to do this. Now how do we figure out the in-between part? This is where we use the XY chart. So I'm going to make one small one right here. I'm going to plug in -1/2 because I don't have any other point that I could possibly test out. And I'm going to try out 1. Now, when I try out -1/2, it's going to be -1/2 cubed minus 2 times -1/2 squared minus 3 times -1/2. So we're going to get -1/2 minus 2 times 1/4 plus 3/2. That's going to be -1/2 minus 1/2 plus 3/2. That is -2/2 plus 3/2. That's going to give us a positive half. So that means it's going to go up and cross to a positive, and then we're going to touch the 0. Now let's plug in a 1 just so we get an idea of what's happening. We plug in the 1, it's going to be 1 cubed minus 2 times 1 squared minus 3 times 1. So we get 1 minus 2 minus 3. That's going to be 1 minus 5, which is -4. So we're going to go like this. And then we get the end behavior. Again, this is a rough sketch of what it's going to look like. And then lastly, I'm just going to write the domain the way we did it yesterday, just to jog your memory. I'm going to write it in blue up here. So as x approaches -infinity, our p of x approaches -infinity. And as x approaches infinity, p of x approaches infinity. So here we have all they asked for. They asked for the zeros, they asked for the graph, and I also wrote the end behavior in the notation that we learned yesterday. So the shapes of the graph near the 0. So the shape of the graph near the 0, the multiplicity of m. If C is a 0 of P of multiplicity m, then the shape of the graph of P near C is as follows. What does it mean by multiplicity? I'm going to do an example in the next slide so I can explain it to you guys. But before we do that, something to memorize is the way the odd graphs looks. Like this, the odd graph has the end behavior of down up for a positive graph. And something to memorize for the even is that for the positive behavior, it goes up, up. Now, if you memorize that and you see that it's being reflected over the x-axis, all you're going to do is flip those arrows. So to finish off the idea of zeros before I go over the example, what is a multiplicity? Is how many times a particular value, in this case of 0, appears as the root of a polynomial when the polynomial is factored. So when we do the example, the next slide, we have P of x equals x to the 4th, x minus 2 cubed, let's say x plus 1 squared. So what does this mean for the multiplicity? We're going to look at the times at the exponent of these terms. So it's going to be x to the 4th is equal to 0. It's going to be x minus 2 cubed is equal to 0. And it's going to be x plus 1 squared equal to 0. Now, you would solve it by taking the 4th root, and you end up with x is equal to 0. But that exponent is what's going to tell you the multiplicity. So x equals to 0, but it has a multiplicity. So with a multiplicity of 4, because there are 4 zeros. There's only one 0, but it means 4 when it comes to the graph. The reason it's 4 is because that is going to tell you whether it's going to cross the x-axis or it's going to bounce off the x-axis. Let's finish the multiplicity and then I'll tell you which one is which. So we're going to here take the cube root and we're going to get x minus 2 is equal to 0. Then I'll add 2 and we get x is equal to 2. But again, it has a multiplicity of 3, so it's going to be with a multiplicity and then again, we're going to take the square on the right side. We get x plus 1 is equal to 0. We subtract the 1, and we get x is equal to negative 1. This would be with a multiplicity of 2. Okay, so how do you know if it's going to quote-unquote bounce or go right through the x-axis? So we have this even multiplicity. I'm going to put even mult for multiplicity. It's going to bounce off the x-axis. And if I have an odd multiplicity, it will cross the x-axis. I'm going to use the example 5 graph to show you what I mean. So I'm going to open a new slide and just kind of regraph it a little larger. So the equation for example 5 was P of x equals x cubed minus 2x squared minus 3x. And when we factor it out, we got x plus 1, x minus 3 is equal to 0. And then we got our zeros to be x is equal to 0, x is equal to negative 1, and x is equal to 3. Now, here we can tell that all of them have a multiplicity of 1. So all of these are odd multiplicities. So when we graphed it, I'm going to make it a little larger. we graph the 0, 0, the negative 1, 0, and the 3, 0. We knew that the end behaviors are down, up. And as we found out, remember for negative a half, we got positive a half. And for 1, we got negative 4. So you know where the points are supposed to be. Around here and around right here. But since they're all multiplicities of 1, let's see if it works. Let's start with the end behavior. We're going to start from the bottom. Going to cross it because it's a multiplicity of 1. It's going to cross it because it's a multiplicity of 1. And then it's going to cross it again. So because they're all multiplicities of 1, or in this case an odd multiplicity, it crosses through the x-axis. Notice how if you have an x squared, for example, just call it f of x is equal to x squared. This is a multiplicity of 2 because even if you equal that to 0, you get x squared is equal to 0. When you take the root, you get x equal to 0. But it's a multiplicity of 2. That's why when you graph this, notice that your point is 0, 0, and the end behaviors are up, up. You're going to start from the up. It's going to bounce right at the 0, and it's going to come right back up. So you guys have been working with these type of multiplicities without knowing what they were. But they always follow that rule. If it's odd multiplicity, it crosses through the x-axis. If it's even multiplicity, it bounces off of the x-axis. Now the black one is example 5, and then the red one is just an extra example, so you guys would see what a multiplicity, even multiplicity looks like, even though you guys already know what a parabola looks like. This is it for today's notes. You also have WebAssign homework on Canvas Open and on WebAssign. But this is it for today's notes.